Hello students, today we are going to discuss about number systems. Computers only understand the numbers. So to understand the language of computers, one must be familiar with the number systems. Now, what are the different number systems are there? We have to know that. First, the number system, which is decimal number system, having base 10, which comprises the number starting from 0 to 9. That means 0, 1, 2, 3 up to 9. So it can be represented by 10 numbers. So base 10. Then binary number system. In binary number system, here base is 2. It can be represented by only two numbers, either 0 or 1. Next one is octal number system. In octal number system, base is 8, starting from 0 to 7. Okay? And the fourth one is hexadecimal number system, having base 8, base 16, zero, 1, 2 up to 15. Okay, so suppose we write up to 9 here, then 10, 11, 12, 13, 14, 15. Now this 10 can be represented as A, 11 as B, 12 as C, 13 as D, 14 as E, and 15 as F. Okay, so these are the four important positional number systems. So in decimal number systems, it consists of 10 digits. Already I have mentioned, from 0 to 9. Okay. Now, how we can change a particular number from one number system, or how we can represent a particular number from one number system to another number system, we will see that. Okay, so first we will convert from decimal to binary and from binary to decimal. Okay, now we will learn the conversion from decimal to binary. To get the binary equivalent of a decimal number, we need to divide the decimal number successively by 2, since the base of binary is 2, and record the remainders. Okay, so let's take the decimal number as 25. So decimal number here is 25 base 10. We have to convert it to binary number base 2. Okay, so we have to divide the decimal number by 2. So divide the number by 2. Here the remainder you have to record. So in this case remainder is 1. Next again divide. Here we are getting here remainder as 0. Next divide it. Here we are getting remainder as 0. Next we are getting remainder as 1. So this process will continue until and unless the quotient is less than 2. So here the quotient is less than 2, 1. So we will stop here and we will also count it as remainder here 1. Okay. So now the final binary equivalent is obtained by assembling all the remainders with the last remainder being the first bit. So this one is the last remainder. It will be the first bit when we will convert it from decimal to binary. So here the binary equivalent of the decimal number will be 1, 1, 0, 0, 1, base 2. Okay. So it's quite easy to convert from decimal to binary. Now we will learn the reverse one. Reverse one is from binary to decimal. Okay. So binary to decimal, in this case, what you have to do here, to get the decimal equivalent of a binary number, we need to multiply the digits with the weight of their position and add the results. So let's take the same example. Suppose here the number is 11001 base 2 and we have to convert it to a decimal number. So what we have to do here? 1, 1, 0, 0, 1. Okay. So to get the decimal equivalent of a binary number, we have to multiply the digits with the weight of their position and add the results. So depending on the position, the first position, second, third, fourth, fifth, but it will start from 0. Okay. And the base here is 2 for binary. So 2 to the power 0 will be their weight. And it will be multiplied by that particular digit. So for this value, the decimal equivalent we will get by multiplying this digit with their weight positions or weight value. That means 2 to the power, the first value to the power 0. Then we will add, for that you will get 0 into 2 to the power, second position it will be 1. Okay. Then you have to add it 0 into the third position, that means 2. The positions we will get 0, 1, 2, 3, 4 like that. So here to the power 0 into that particular value, to the power 1, then the particular value, 2 square, then particular value. Then for 1 we will get 1 into 2 cube plus for this value 1 into 2 square. Okay. So here 2 square, here you will get 16, 2 cube you will get 8, multiplying by 0 always gives you 0, for the same reason it is 0, to the power 0 is 1, so 1 into 1, 1, so 16 plus 8 plus 1, it is 25. So ultimately we are getting here the equivalent value as here 25 base 10. So I think now it is clear how to convert from decimal to binary and binary to decimal. Now we will learn conversion from decimal to octal. Okay. To get the octal equivalent of a decimal number, we need to divide the decimal number successively by 8. Since here the base is 8, and also here also we have to record the remainders. So suppose the decimal number is 395 and base here is 10. So you have to convert it into the octal number where base is 8. So this 395 number you have to divide by 8. Okay. And if we divide 395 by 8, we will get here 49 and remainder here 3. Next, again if we divide it, then 6 into 8, 48, remainder as 1. And this process we have to continue until the quotient is less than 8. So here the quotient is less than 8, 6 is less than 8. So here you can stop it, or for your more actually clarification, you can show one extra step. Like if you divide it, you will get here 0, and obviously here the remainder will be 6. So you can stop here up to this and show it here like 6, 1, 3, or you can show it that you are getting 0 as quotient and getting remainder as 6. Both are okay. Okay. So here also the last remainder will be the first bit, like the previous one. So if we represent it in octal format, so the result will be like this is the decimal number, and 6, 1, 3, base 8. This will be the octal representation of that number. Okay. Now if we want to do the reverse one, that means from octal to decimal conversion, what we have to do? Okay, let's consider a octal number. Here suppose the octal number is 1, 3, 2, 5, base 8. So you have to convert it into the decimal number where base will be 10. Okay. So here also the same thing. Here the number system consists in case of octal number system 8 values where 0 to 7 it will take. Now we will do the conversion from octal to decimal. So let's take a number in octal. So here 1325 we have taken, base 8. So we have to convert it into decimal. So what we have to do? Here we know that in octal number system it consists of 8 digits starting from 0 to 7. That means 0, 1, 2, 3, 4, 5, 6, 7. Base here is 8. So here also each digit position represents a power of 8. Okay. So since here the number is 1, 3, 2, 5. So depending on their positions, it will be multiplied by 8 to the power this particular value. So how it will be represented? Suppose here this 5 position here is the first position, that means starting with 0. So the weight here will be 8 to the power 0. It will be multiplied by 5. So here 5 into 8 to the power 0, it will be multiplied by that particular digit 5, plus 2 into 8 to the power 1 for this 2, plus 3 into 8 square, plus 1 into 8 cube. Okay. So each digit position in this system represents a power of 8. So here the 0th position, or we can say the first position actually represented by 0. So 8 to the power 0, that weight factor will be multiplied by the digit. Here 8 to the power 1, that weight factor will be multiplied by the digit 2. Okay. Then weight factor 8 square will be multiplied by 3. Then weight factor 8 cube will be multiplied by the digit 1. Okay. I think it is clear. So we have to now sum up all this and get the value. So for the first one we will get 512 plus 3 into 64, that means it is 192, plus 2 into 8, that means this is 16, and plus 5 into 8 to the power 0, and that means 5 into 1, that means 5. So ultimately we will get the value 725. You can sum up here 5, this will be 725 base 10. So this is how we can convert a particular octal number to its decimal representation. Okay. To get the hexadecimal equivalent of a decimal number, we need to divide the decimal number successively by 16. So let's take the decimal number as 2, 6, 9, 9, 10 and convert it into hexadecimal number. So here we need to divide the decimal number by 16 since base of hexadecimal is 16 and record the remainders. So divide it by 16. See, if we divide it by 16, we will get here 1, then 6, then 8, and the remainder it will be 11. Okay, you can divide it and get the value. Now again we divide this number 168 by 16. So here first it will 1, 16, then getting 0, 160, and remainder it will be 8. So here we will continue the process until the quotient is less than 16. Here 10 is less than 16, so we can stop here, or you can show another step, another extra step for your more clarification, that you can write here and show it as 0 quotient, and remainder obviously it will get it will be 10 as a remainder. Okay, now we know that in hexadecimal format after 0 to 9, from 10 we have to represent it by like 10 as A, 11 as B, and so on. Okay, so here the final hex equivalent is obtained by assembling all the remainders, with the last remainder being the first one. So it will be like this. So if you convert it like from this decimal number to, so here it will be, instead of 10 we will write here A, then 8, instead of 11 we will write here B, so A, 8B, here the base is 16. Okay, now the reverse one if you want to do, that means if you want to convert from hex to decimal, then what you have to do? Suppose here the number is 7CE. Okay, starting from A, we know that A, 10 is A, 11 is B, 12 is C. So here C will be 12 and D will be 13. So E will be 14. Okay, so depending on the position value, here we can write here weight as like it will be multiplied by 16 to the power 0, then it will be multiplied by 16 to the power 1, then it will be multiplied by 16 to the power 2. Okay, so ultimately what we will get? We will get 14 into 16 to the power 0 plus 12 into 16 to the power 1 plus 7 into 16 square. So we will get here 7 into 2, 5, 6 plus this 16 to the power 0 means 1. Okay, so after calculating this value, ultimately you will get the value as 6 7s 2, then 9, then 7 1 2, this one is 192, this 14. So ultimately this is 4 to 6, it will be 1998. Okay, So you can write here like this. So ultimately 7CE base 16. After conversion, if you want to convert from hex to decimal, we will get 1998 base 10. Okay.